Okay, so welcome to this lecture on, I hope, digital circuit design. Otherwise, I'm in the wrong room, and some of you might be as well. So, and today's lecture will be dedicated to memories. My name is Srdjan Čapkun, and I'm a professor here in the computer science department. My primary research area is actually security related to hardware and wireless communication systems. And I happen to be involved in this course as well. So I'll try to excite you about memories and show you with few examples why memories are actually quite crucial, not only in terms of performance, but also in terms of the security of today's systems, right? So, but just to give you a little bit of an overview where memories are going, I found this clip this morning from Intel, because Intel recently introduced a new type of memory, and by the end of today or tomorrow, you should be able to, at least on a high level, understand why Intel was working on this so hard. And by recently, I mean they actually announced it beginning of this year, and they're pushing it now into their processors. So a little bit, I mean, I apologize for this video being a bit more kind of commercial, because obviously Intel does this for money. So, but it's also nicely done. So I hope it motivates.
Memory technology was invented, but that's about to change.
The quest for getting data closer to the CPU, or solving the problem of the data and the CPU not always being together, has been around since the origination of computing, since von Neumann originally did some of his work.
Probably the last real breakthrough in memory storage, if I was to characterize it, would have been in the early 70s. I mean, if you look at the three main kinds of memory that exist today, the predecessor of flash was really the UV-proms that were developed in that time period. DRAM was developed in the late 60s, and it still is fundamentally the same. Really nothing substantially new has really occurred since that time period.
All the while, data growth is exploding, roughly doubling every 2 years. And those massive volumes of data must not only be stored, but analyzed to extract meaning, value, and insight.
We all know that there's more and more data in the world. The more data that there is, the more processing you're going to want to do on that data.
Faster storage is important to computing because computing is done on data, and data is put in storage. The longer it takes to get to that data, the slower the computing goes.
So high-performance computing has always been very data-hungry, and the larger the data sets we can handle for HPC applications, the better science we're going to be able to do.
But therein lies the problem. Even today's fastest storage memory is roughly 10,000 times slower than the fastest CPU memory, resulting in a performance-crushing penalty each time data is accessed from storage. We desperately need faster storage memory.
Computer architecture from its days of von Neumann hasn't changed significantly, in the sense that it still has the same basic components.
There are a bunch of memory technologies in a computer. All the way from registers in a CPU. There are actually 3 levels of cache in a CPU die itself, where some of the levels are closer and more expensive and faster, and then they get bigger and a little bit farther away from even inside the chip, there's close and far. And then you get off the chip, and today you have DRAM, and then you have NAND SSDs, and then you could have hard drives also that are even farther away.
So we want to get as much of the data as close to the CPU as we possibly can. And if we can get that data to be faster, then the CPU waits less for that data.
For decades, engineers around the globe, including multiple teams at Intel, have been racing to design that next breakthrough memory technology. Many have questioned whether it's even possible. But now, Intel engineers have realized that breakthrough.
Okay, now I have to cut it off because it's getting a little bit too... I'm not paid by Intel to show this. So, but however, this we will touch on this piece of technology because it is a new way of accessing memory, and you will actually immediately see why it's much faster than something that we have been traditionally using and are still using in most systems. Of course, it has its pros and cons, and they are painting this kind of wonderful picture, right? That might not exactly hold. I mean, people are already testing this Optane technology. I mean, another name for this Optane technology is actually 3D X-point memory, right? So Intel kind of brands it as Optane technology, and it's essentially a different way of accessing different memory cells. Okay, but in order to understand this entire story, and especially the part of this video that talks about proximity of memory to the processing. So this I think is the most crucial thing, right? I don't know if you missed it, but the thing is that so far in this course, you have been always thinking about, you know, clock cycles and how fast your processor can run, but it's actually the problem today is not really how fast your processor can run. It actually can run as fast as we need it to run for most applications. It's just that it has to wait for a long time to fetch something from memory, because our RAM, right, our working memory, access to this memory can be 2 orders of magnitude longer than the clock cycle of your processor. So of course, then all kinds of optimizations within processors have been happening to fit more instructions to be executed while you are waiting for some data to be fetched. But this is not optimal, right? Ideally, you would want this latency of access to data to be reduced, so that when you run something for some high performance computing task, that you get this access immediately, right? And so if you look at today's systems, because of these latency issues, the designers of processors have been storing memory ever closer and closer to the CPU, and this here shows it quite nicely, right? So you have registers which are really in the processor, and they're super fast, because you have seen this in your when you are developing the processor in your exercises, that the access to these registers is essentially in hundreds of picoseconds, right? I mean, that's what you get because it's in the processor. To all kinds of cache, here the distance to the core and also the sizes of these caches are telling you how big they are, and also the latency of access to these caches. These are just memory elements, right? Cache is essentially just a memory element, which is smaller and also done in closer to the CPU, because, well, think about it, 30 centimeters is 1 nanosecond. So any kind of distance, real physical distance, and also any kind of complexity in terms of size of the cache will impact how fast you can access it. And so if you can shed off any percentage of the distance or of the size of this memory, that's a performance benefit. There are obviously also trade-offs, because if something is big, then it will require more time to access, right? Because you will have essentially more elements inside to activate in order to access the data. So you also have to have a larger address to address that larger piece of memory. So the access to larger memory will take more time. So this means that the design imperative has to be that you get the memory close to the CPU. It has to be small, and it has to be in order to have it fast in terms of access, meaning low latency. But obviously this is an issue, because if you have a very small memory close to the processor, then it will store only maybe some few megabytes of data or kilobytes of data, right? That will sit close to the CPU. But which data should you store there, right? Then you have to again optimize, right? Because your entire program will not fit in the cache. So people have been starting to develop these cache hierarchies, right? Where you have L1 cache, L2 cache, L3 cache, which might even be shared between different cores, in order to compensate this for these issue in terms of access. And of course, on the other side, there have been pushes like the one that you have just seen from Intel, to essentially merge all types of memory into one. So to build a type of memory that's fast enough that you don't have to have a hard drive and a working memory, but essentially your hard drive becomes the working memory. It's persistent memory that's fast enough, because that's the ideal goal, right? I mean, you would like to have something that retains the data even when you switch off the power. Why not? You know, there's no reason that we would have this kind of memory that we have now, where you lose data when you switch off the device. So this is not something that we wanted to have. This is something that we have to have, because we couldn't build memories that had persistence and at the same time that had fast access, right? So what are we going to discuss today? We are going to discuss different types of memories, and seems to be kind of trying to make it a little bit better. And also the implications of different types of memories. It seems that it's not super good, so we'll have to live with this VGA or whatever this is, distorted image. So we'll go over common sequential building blocks like counters and shift registers, which are very commonly used to build registers, essentially registers and register files. And also we'll go over organization of memories, how to access memories, and different memory technologies and their challenges. So I included this link in the slides, so I will update the slides later today so that you have all the things that I added since the slides were posted. So common sequential building blocks. Well, typically, you know, if you want to build these kind of simple blocks, and you probably have been exposed to them already, these are various counters or serial to parallel converters, which we actually need to build memories, and also we need them to build registers like parallel in, parallel out, for example. Those are the kinds of registers that we want to build, or various counters. Then, of course, the simplest thing that we can build would be something like this, right? So these counters are very simple elements where we take the output and we connect it to the input, and there is always a 1 here. We have an adder here, and now on the rising edge of the clock, the state of this element is going to be updated. So every time that you have a rising edge of the clock, you will update the state of this element, and it will increase by 1, because one will be added every time that you run this cycle. Actually, 1 is essentially added immediately when n is updated. So this comes here, adds with 1, a new n waits for it, and then when there is a rising edge of the clock, you load the new value, and the new value is now available at the output, and the n plus 1 is waiting on the input. And of course, if you want to cycle through numbers, or if you need some digital clock displays, or a program counter that keeps track of current instructions, we will implement such a simple circuit that you already know, right? Another very common element that's used in registers, or to build these kind of small memory components that we need in the processor, are shift registers. They're actually very popular in generating any kind of randomness in systems, not cryptographically secure randomness, but they are actually a very simple element to generate sort of a randomness that adheres to all statistical tests, or at least, a series of statistical tests, and they work in the following way, right? So the implementation of it's essentially a serial to parallel converter, right? So you put an input, a a value, right? And now, as you add more values at this input, the previous values get pushed and stored in the registers that go from left to right. And in the end, if you have stored, let's say, n values, then these n values are going to be available here from Q0 to Qn minus 1. And so you, in fact, have a serial to parallel converter, right, which takes a serial input S in and outputs these value in parallel, right? Now this is important because, of course, now you can get these values, so you can say, well, it's all the same. Well, this is actually not all the same. Having data in serial or in parallel form is actually not the same. If you think of a design of any kind of operation, right, sometimes you want to have access to data in a single cycle, and that you can only have if you have this data sort of stored in an element that gives it to you in parallel, meaning that all the bits are available at the same time upon some rising edge of the clock. So this kind of a conversion from serial to parallel is very important, and it constitutes one of the basic elements of storing bits, because you actually want to load something. So imagine you have a process and you have ADC converter. So this process can be any kind of analog process in nature, right? And you are measuring every microsecond, let's say, and now you're pushing this into your register. Well, that's essentially what happens then, right? All this data is now stored, meaning that now it's available also immediately for some other processing. So after you have stored it, you can access it after you have sort of successfully finished measuring, you also have it for immediate processing. So, and of course you are shifting this value on each clock edge, right? I mean, this is clear due to this element. And this is just a symbol that indicates that you have here serial in, serial out, and also here that you're going to obtain all the values that were pushed in at the same time. Now, of course, this construct can now be generalized, and now you can build something that has a parallel load or a serial load. So essentially, it can act as a serial to parallel converter, right? Which is something that we already had, where you have S in as input, and then Q 0 to n minus 1 as output. But it can also be, you can also now build a parallel to serial converter. So let's say that you have a set of values, and now you want to output a value each clock cycle, another value, or whatever your other logic dictates. You know, you want to have one value being pushed out as the time progresses according to time or some counter. And what you can do is build this kind of a construct. So when the load here is 1, this acts as a normal n-bit register, right? And when load is a 0, it acts as a shift register. And it's actually fairly easy to, I mean, it's easy to understand why this happens from this diagram. So this is the load, which essentially controls these multiplexers here that will determine what will happen, right? So, of course, you know, these are very simple basic elements, right, that we can use in processor, and as you have seen, you need something like a program counter, so you need counters in the processor design, and you also need these kind of shift registers in many kind of specialized systems. But maybe most interesting elements that we are building are actually memories, right? So memories that are supposed to store large quantities of data, and of course, as you have seen, they allow you to store data and work on stored data, because we can store programs as well as data on which these programs run. And of course, these kind of numbers here are pretty much redundant today, because I'm sure that all of you know how much a single HD picture costs in terms of storage, right? But I think it's an interesting thing to look. I mean, an interesting thing to look at here is the following. So this is the Intel processor in 45 nanometer technology, right? So, and if you look at it, these are the larger memory blocks on this processor, and this gives you an idea. And I'll let you figure out which one, what these memory blocks are. But this shows you how much memory is actually present in these processors, right? It's really at the core of the operation of these systems. So how do we actually store data in the end, right? So of course we have seen that flip-flops, right, or latches, they are very fast. They give you parallel access, so that's essentially the fastest type of memory that you can have. And they typically look like this, obviously not with two transistors, but they are typically built with 20 transistors. Right? Depends on the particular technology, but they're actually quite expensive to build. And that's why this is it's very fast memory, it's volatile, but it's expensive, and you cannot have too much of it in the end in the processor. Not only because of the cost, but because you cannot scale this access to such registers, right? And of course, this can be built in a particular way with transistors. Then we have static RAM, so SRAM, which we will cover in a bit. Right? It's fairly fast, but we can access only one data word at a time. It's a bit less expensive. It costs only 6 transistors, so we are already going down. So we have something that's not as fast as a flip-flop, and can access only certain limited amount of memory of data, and it's a little bit less expensive, right, to build. And then we have DRAM, which is even slower, which actually requires, unlike SRAM, it requires some refreshment of data, right? However, it's somewhat cheaper. So essentially, 1 bit is only 1 transistor. So the cost is lower, but it's lower in terms of access, and reading destroys content. So this means you need some refresh. So you essentially need some special processes to handle that. And static RAM is somewhat faster, right? And typically you would use SRAM as opposed to DRAM when it comes to performance. Flip-flops you would typically use only to implement something that's really in the CPU itself, some sort of registers that require pretty fast access. So other storage technologies are much slower. Access takes a long time. So we are talking about differences of 10,000 to 100 to 1 nanosecond per in terms of access, in terms of memory access. We'll cover this a little bit more when we discuss caches and cache hierarchies, most probably tomorrow. So what is the general organization of memory? So typically we access memories by essentially using arrays, right? Which means that we organize it in a way that we have an address which comes here, which has some n bits, and we get some n bits of data as a result at the output of this array, right? So the memory will consist of these kind of memory of memory arrays, and this address selection will determine what comes out of here, right? So I guess this is a fairly simple example. I don't know what more to tell you on this slide, right? I mean, of course there are some definitions in terms of depth and width and so forth, but it's actually quite straightforward, right? You have an address and you read out the data as a result. So each address corresponds to this data here. Yeah. I don't think this is very brainy, so I think I'll skip it. Okay, good. So we also have different types of memories, like volatile and non-volatile. And volatile types of memories are those that will lose data when the power is off. And this is because they're essentially active elements that are holding each other in a particular state, as opposed to non-volatile memories that keep data even without power, and those need to be built in such a way. So initially, obviously, these were hard drives. There were some mechanical elements that were writing onto a material of sorts, and then you could read from it. But today we actually have different types of transistors that allow us to store, to keep data even without powering them, and you probably have them all in your computers. These are SSD drives, right, which are based on flash technology, right? So SRAMs are probably quite simple. So they are volatile. They store data by cross-coupled inverters, right? So essentially, each of these inverters keeps. So these two inverters keep each other in a particular state, right? And so if you kind of unfold this, you can see it here. So you can keep. I mean, you can use these elements as well, or these elements here. It doesn't really matter. So you use two elements that keep each other in a particular state. So that, and this state is stable, unless you flip the state, and then you would have Q and Q bar inversed here in this figure, right? So they're historically called random access memories because data can be accessed in any order, right? Unlike magnetic tapes that had only serial access, right? So this is static random access memory. And given that it's built from these kind of elements, active elements that keep each other in a particular state, it doesn't need any kind of refreshments, right? It doesn't really have a charge that indicates the level at which that indicates a bit 1 or a 0 within this memory element. So if this is your memory cell and holds only one value, you don't actually need to refresh it, right? The voltages that are applied to these memory elements will just keep them in this state until you flip them. Now, unlike SRAM, DRAM is actually literally built out of small. But of course, sorry, this costs you then several transistors because it takes you several transistors to build such elements. So for each cell, you, for example, need 6 transistors to build something like this in a particular technology, right? So, and here in DRAM, what you have is literally that you are charging a small capacitor. So this small capacitor is controlled by a transistor. So if the capacitor is charged, you have one state, so you are storing a bit 1. If a capacitor discharges, you're storing bit 0. And now the problem with this kind of technology is that, well, obviously this is a capacitor, and your transistor that gates this capacitor from the rest of the system is not perfectly tight, and therefore it's going to leak some current. And as it leaks some current, what might happen is that this capacitor actually loses the state. And if it loses the state, then this bit has been accidentally flipped, and this doesn't speak well in terms of the integrity of your technology. And as we will see this later, actually with more and more denser packing of DRAMs that we have today in our systems, we have started to see these kind of issues, right? I mean, the different elements just randomly flip. And you don't notice it because there are error correction mechanisms and error detection mechanisms in the memory controllers, but essentially these are not super stable systems, right? Some bits will flip while you use your system. And in order to prevent this leakage, we have the system actually refreshes this state, and the refresh rate can be, for example, in the order of 64 milliseconds, right? That you have to refresh the state of these capacitors. Obviously, also when you read, you might also leak some charge. So this is just to illustrate the DRAM kind of setup with different lines that control different cells, right? And we'll illustrate how this works on a different example, but just to give you an idea of how this is stacked. Then the nice thing here is that you can densely pack this, so this is literally one capacitor per memory, per bit, right? So how would you organize your memory? So any of these memories are organized in the same way. So these are all 2D memories. And the reason that I'm mentioning that they're 2D memories is because, well, the Intel's proposal now is to use a third dimension in order to operate over these memories. So these are all 2D memories. So you have an address here, and the address selects a word line. And this word line, so you have this decoder here, and given the address, a particular word line will be activated, and then as a result, this word line is going to, and you are going to be able to read a data that only pertains to a particular word line. So we have a word line and we have a bit line, and the word line obviously corresponds to the address. So each address is one word, and this word, and within this word we have bits, right, which are placed on these bit lines. And so this, if you go back here, you can see the same structure here. So when you now activate a word line, so let's say that you want to read from address 10, so 10, right? I mean, you activate this word line, and as a result, you will be able to read these 3 data bits, which correspond to the word located at this address 10, right? So this is the way that all of these memories work, irrespective of the way that the cells actually work. And the reason why they work in this way is that, well, here you have some transistors, and these transistors are going to be activated by activating a particular word line. And then if you are activating this transistor, as you can see here, for example, if you activate this word line here, you will open these transistors and allow this positive charge from this capacitor to be measured down here, right? So you activated this word line, and now you activated these 4 transistors. As a result, you can read out whether this first, second, third, and fourth capacitor contains any charge. You measure it here, and if you see that they contain charges or not, that's what indicates bits 1 or 0. So, yeah, and essentially if you look at now the design of SRAM, it's not that different, right? You are again activating a word line, which allows you to measure the state of this SRAM, of these SRAM cells, and I'll let you figure out how you can do that. Yeah, so the read-only memories, right, are non-volatile, and they can be therefore made much denser. So essentially, if you have a non-volatile memory, you essentially just have a grid of wires that are kind of fixed, right? So the intersections that are fully fixed. So, and it was very common to have ROM elements or read-only memory elements in different systems. And today, what we have is actually typically programmable memories. So we do have some read-only memories, but the technology advanced, and we can actually program them. Now there are different types of these read-only memories that are programmable in the sense that when you ship them once, you ship them empty, and now you can program them. When you program them once, you cannot erase them anymore. Or what you can do is you have the erasable proms. This means that you can use some ultraviolet light to erase the entire content of the memory, and then you can reprogram them. Or you also have EPROMs, so long E, 2 E's proms, right? That can be erased several times, so they can be electrically erased, right? And these are typically used today for any kind of firmware that you have around in embedded devices, because you can reprogram them. Of course, you know, in ROMs, the things can be infinitely simpler, right? So you can have wires which are connected or not, right? So when you have an address here, which is 11101, so which activates individual lines, where you have dots, you're going to have ones. Where you have no intersection, you have zeros. So this is also pretty simple to build, and it's pretty stable because it doesn't necessarily have any kind of active elements if we are really talking about a pure ROM storage. Now the nice thing about these kind of these kind of designs, not only when you talk about ROMs, but when you talk about any kind of a design of memory, is that memory in the end, given that it includes a decoder and the storage, what it represents is essentially a general element that can implement any kind of a logic for you. So, for example, in this case, we have an address here, and now as a result of this address, we can implement an addition or a multiplication of any of these bits here of these two bits here of the address. So A1 and A0 being the bits of the address, and given the configuration that we have here of a memory element, we can implement this kind of logic. So data element 0 is going to give us A1 bar times A0 bar, and so on, right? So because just by the way that we configure these kind of elements. So we can actually implement a logic function using any kind of a memory array, right? And in the end, you know, if you do that, if you implement logic with memory arrays, what do you get? Well, you essentially get lookup. You get an implementation of logic using lookup tables, and this means that you are using, well, a decoder, and you use the address as an input into this computation, and use the bit lines in order to have an output. And your truth table is reflected very nicely in the memory element that you have here. So your memory element here clearly corresponds to so this bit line here clearly corresponds to the output that you want to be selected, because here it's fairly simple. 1 1 will correspond to 1, 1 0 will give you as an output 0, 0 1 0, and 0 0 0, and this reflects the truth table that you want. So the integration of these kind of decoders and the memory elements which we use can enable the design of any kind of a logic. And now, is that okay? Okay. So it's just a lookup, right? You're saying, let me implement this truth table as a lookup. This means, okay, 4 0 0, give me as an output 0. How do I do this? Well, very easy, right? You encode all possible input states here, right? In these addresses, right? These addresses can be 0. So this input can be 0 0 0 1 1 0 1 1. So this reflects how many bits you need from the truth table, and here as an output you store whatever you want. So essentially you can implement arbitrary logics within a lookup table. And this shouldn't surprise you, right? So now the question is, why shouldn't this surprise you? I shouldn't ask any questions, I guess. I just go. Yeah? Yeah, because you use it all the time, right? I mean, this is how your FPGAs are actually built, right? Your FPGAs do exactly that. So they are not, I guess this is an analogy that some of you might have, that there are, little people living in these FPGAs that rewire things as you send the bit stream in. But I would guess that doesn't happen, but instead what happens is that you have these lookup tables, right? And these lookup tables, typically these 3 lookup tables per configurable logic block that allow you to implement any kind of a logic function that you want, right? And the basic principle is exactly this, right? I mean, you don't have to care that much about the complexity of the design or Karnaugh maps or any kind of sophisticated tool that will tell you how to do this and that. What you have to do is just to express what kind of logic do you want to be implemented within your lookup table, and it literally reflects the truth table that you want. And then, of course, if you now can build these kind of memory elements that can take as inputs addresses and give you out the data, of course you can implement memories that have several ports, right? And where different ports are activated differently, right? And they give you different outputs, right? I mean, so you read essentially from different registers, or you write into different registers. And this is what you call and what you have seen in this course as register files that store essentially the smallest amounts of data that you push around within your processor, instructions and data that you are processing on. So when you have such arrays, that's essentially what sits in your device, in your CPU. And of course, it's not terribly complicated in Verilog either. Now, very often when you talk to okay, so I guess I'm legally obliged to give you a break. So let's take a break and then let's continue. Okay, so good. I guess no one installed. Okay. Break. Very good. So. Aside from the memory elements that we have seen, obviously there are memory elements that are quite interesting because they try to provide some persistence at the same time while using transistor technologies, and if you look at this picture here, so the flash memory actually use a different type of transistors, and these transistors allow them to trap a charge within a gate, so within a second gate of a transistor. So typically you have your common MOSFET transistor here, where you have a gate, and now you have to apply some voltage to this gate in order for things to happen, right? And now in the flash cells, what you have is you have a second gate here, and this gate here can trap a particular charge. So if you apply a higher voltage, you will trap a charge within that gate, and even if you now remove the voltage from the gate, this charge here will make sure that the transistor remains in a particular state. And now, obviously, it would take a much higher. It takes a high voltage to kind of breach these kind of barriers in order to put charge and also remove charge from these gates. Now, this of course leads to an interesting phenomena. I mean, eventually it actually destroys this cell. So it's this kind of transistors. They don't really. You cannot write to them and read from them an infinite number of times. So you have a finite number of times to use them. And these kind of technologies like NVRAM and so on are quite common in in components such as, let's say, a TPM. A TPM is a trusted platform module that sits in your computer today and can enable you to seal some confidential data, works with your BitLocker in order to encrypt your hard drive, which is what most of the operating systems today leverage. It also can generate keys for you, generate randomness for you, can sign things for you. This kind of NVRAM is leveraged for state protection by newest Intel extensions called SGX, which are software guard extensions in the processor, so special types of instructions that are used to isolate the execution on the processor and to encrypt memory. So those kind of memories are actually in your system, and they're not only used for SSDs, right? They're actually used also for other types of operations. And those memories. So we did a test recently on one type of such memories, and after 100,000 rewrites, the memory was dead, right? So if you aggressively go after it, it took us a couple of days to aggressively write, and then after that the memory didn't work anymore. So yeah, so how do you actually program these kind of memories? Well, there are several ways to program them, right? You can also, the nice thing about them is that they can actually be programmed to different levels of voltage, right? So essentially different levels of charge, and that allows you to have to store more information within a single cell. So you, instead of just programming the data in two states, right? You can program the data in several states, right? So you have these kind of memories like single level cell, multi-level cell, triple level cell. So as you can see, obviously now the ranges of voltage that you can use in order to charge individual levels will determine how do you encode your data. So if you have this is a charge on the floating gate in case that you can't see this. So this charge on the floating gate, is the smallest for 111, and then if you want, so you encode 3 bits per level, and these little distributions here indicate essentially the range within which you need to charge in order to indicate a particular value, right? And you have some guard bands in order to guard against any kind of errors. And now, of course, you will often hear about multi-level cells, single-level cells, and these endurance number here, as you can see, might change as a result because you are stressing this particular type of technology. So. So the data retention is not an issue, right? This is a persistent type of storage. So again, even if it's a transistor, so it doesn't. You can see it as an illegitimate child of a transistor and a capacitor, right? Which essentially traps these. So this charge here that you have in the gate that I showed you, turns this into a. So okay, it would be a little bit complicated to explain, but again, you can see this as a kind of capacitor combined with transistor. So again, this charge levels can be different, and people are using it actually for all kinds of funny purposes. So recently there was a paper and a related product that is actually hiding information in these. Within the distributions of these levels, right? So, for example, if I want to hide some information on my system, so that when I'm crossing a border or when I'm going somewhere, even upon forensic inspection, no one can figure out that I have this information present in my system. What I can do, I can now take this single level cell and I can write it to a particular voltage level, meaning I will have a particular charge on the floating gate that will fall within the distribution that is expected, but this charge level will indicate some information. So it will allow me to encode information within the distribution of this charge. And now this I can use to hide information. So when you're reading now the data from my disk, well, you will read ones and zeros, but anyone who has a particular key or has some secret will be also able to read this extra information that's encoded in the charge levels on the floating gates, right? And of course you can apply the same idea to multi-level cells or triple-level cells or whatever, right? I mean, so this is the I thought that it's kind of useful given given that flash memories are pretty much everywhere. So the last piece of technology that I think is kind of interesting is this 3D X-point or Intel Optane technology, right? Which I will also present to you through a video because I think they explain it in a nice way, and I think it's kind of cool to see it. So bear with me.
Ever wonder why your computer is so slow?
A little bit of
Chances are
advertisement
your storage
again,
device
but
is the problem, slowly responding to your processor's data requests and causing it to work at a fraction of its potential. Eliminating that bottleneck requires memory that is fast, dense, and non-volatile, so your data doesn't go away when your power does. DRAM memory is great because it's very fast, but it's volatile. And unlike many silicon components, DRAM density isn't doubling every 2 years, so it's hitting a wall. On the other hand, NAND memory, found in today's SSDs, is both dense and non-volatile. And while it's fast compared to other storage technologies, it's still much slower than DRAM. But get ready. We're about to shatter today's rules in a very big way, thanks to some breakthrough engineering we've been working on. Now, for the first time ever, we'll be able to equip computers with memory that's faster than NAND, and more dense than DRAM, and non-volatile. Intel Optane technology combines a next-generation non-volatile memory called 3D Crosspoint memory with Intel's advanced system memory controllers and interface hardware and software enhancements to bring amazing new computing possibilities to a variety of markets. So, how'd we do it?
Okay, I think that's the interesting part, how they do it.
Dense, we packed lots of capacity into a tiny footprint. We started by slicing sub-microscopic layers of materials into columns, each containing a memory cell and selector. Then we connected those columns using an innovative cross-point structure consisting of perpendicular wires that enables memory cells to be individually addressed by selecting one wire on top and another at the bottom. We can stack these memory grids three-dimensionally to maximize density. And whereas DRAM requires a transistor at each memory cell to access or modify the cell, making DRAM big and expensive.
Yeah, I think this is an interesting design. So obviously it's kind of obvious that you would, if you have an ability to do this in such a small scale that you can that you can essentially select by having such a three-dimensional structure. So one perpendicular to another, right? So you have these two lines that essentially determine which memory cell you will access, right? And then you can read and write to this memory cell. And as you have probably heard, I mean this operation actually doesn't really require you to have a transistor, right? Because now instead of having a switch to do the selection, what you have is at the nano level, you have wires which when activated, they will essentially do the selection of the location from which you want to read. And and I guess you can sort of filter out all the other Intel mumbo jumbo, but I think somehow, being an engineer, I guess 20 years ago used to be, people didn't do this kind of stunts, publicity stunts, Apple style. But these days it seems to be a must.
Each memory cell can be written to or read by simply varying the voltage sent to its selector, completely eliminating the need for transistors. This simple, stackable, transistorless design enables us to deliver greater capacity than DRAM in the same space. When it comes to memory performance, low latency is the key, especially for today's demanding workloads. Intel Optane Technology's latency is much shorter than NAND memory, eliminating a significant portion of the performance penalty for each data request. This makes Intel Optane technology ideal for all devices, applications, or services requiring fast access.
You know, if you don't have Intel Optane, you will not be able to sleep tonight. You want to watch it till the end?
Disruptive memory technology designed to change the face of computing with an unparalleled combination of speed, density, and non-volatility.
Yep. It's unparalleled, it's great, it's amazing. So, good. Buy today in selected stores. Yeah. Okay, very good. So but I wanted to show this because it's something that, first of all, came out now, like a few months ago, and it also kind of makes you think that, makes you think about possible designs of memories, right? It's not all about transistors. You can obviously, if you have access to different kind of technologies, try to realize these kind of selectors through either 3D structures or some other means, right? And these kind of ideas, of course, have been floated in the past, but they have to be combined with the available technology at a particular nanometer level, and then if they can be built, then we get this kind of products out. So there is nothing fundamental. There's nothing else to say about this at this point. People now started playing with this and starting to validate all these amazing claims that Intel is making. Right, and we are still trying to figure out, okay, how good is this, and how we could potentially use it. Maybe another thing that I find kind of fascinating about memory is, given that I work in security, then anything security related is fascinating to me. So here's an example of issues that you get when you start densely packing things. Did anyone go to Onur Mutlu's inaugural lecture, or someone is? Some of you went, right? So I guess he talked about this row hammer attack a bit. So for the rest of you, no, he didn't. I was there. He did. Okay, so he talked about this grand issue of memories and so future computing architectures, and then he mentioned, maybe you missed it a bit, the row hammer attack. So what is a row hammer attack? So it's something that Onur actually came up with. In one way, right? He essentially noticed that, people noticed already over time that as DRAM cells, so we're talking about DRAM memory that obviously stores data using small capacitors and also small transistors. They're trying to, all corporations are trying to essentially pack these transistors and capacitors as tightly as they can, because then the overall latency of access and also the cost and the size, they go down. So what you want is if you start scaling this beyond a certain number of nanometers, then these DRAM cells, they become more unstable, but also more vulnerable to cross-cell interference. So people started noticing that these systems started to fail. Like every once in a while, you would see that that 2 bits that sit in 2 neighboring cells interfere with each other. So let's say you start reading many times a bit from one cell, then the bit in a neighboring cell gets flipped as a result. And these are the effects that start happening when you pack things super tight, densely, right? So then in 2004, one of the first papers came out talking about flipping bits in memory without accessing them. Now, why is this security relevant? Well, here's a very simple reason, right? So maybe someone can tell me why is this an issue for it? Why could this be an issue that reading one bit aggressively flips another bit? Does this bother you? Except for integrity, robustness of your computation, is there something else that can happen? Yeah? Okay. But I could do that. I mean, I could turn this off in any case. So
you could flip bits in write protected cells.
yeah, exactly. So I think maybe to kind of highlight it a little bit more, to rephrase it a bit, if your memory is divided between something that belongs to the kernel or the OS, right, and something that belongs to some application, then what can happen essentially is that if I pick a bit, in my application space that happens to be adjacent to it happens to be in the neighboring cell as a bit that sits that is actually controlled, a bit of a memory that's actually mapped into the operating system. Now, if I aggressively read this bit here, I will flip this bit from 0 to 1. And maybe this flipping of the bit from 0 to 1 can allow me to do privilege escalation, right? So I can now, as an application running with some user privileges that is limited, right, because the operating system limits me from doing something, I can gain root access. And based on this observation that the memories are vulnerable to this kind of manipulation, people actually built a whole bunch of attacks based on what is called a row hammer attack, right? A row hammer attack because you are essentially hammering you're reading, and they called it hammering, right? So you're essentially aggressively reading bits in a particular memory cell, and then you cause the other bit to flip, right? So you read like whatever, millions of times. You can do that because that's a memory cell that corresponds to the memory that's that's controlled by your application, right? And you flip a bit in a memory that's controlled by someone else. And memory isolation is actually the holy grail of security, right? I mean, one of the most important things in security is when you're running several things in a system is to isolate the memory from one process from the memory of another process, because, well, everything is done in memory, right? The code is there, the data is there, so be it for data leakage or integrity protection, that's essentially the key. And so, so people showed that this could be done. So how can this be done? Well, as I just explained to you, right, so this here row of a memory cell is hammered aggressively, right? And these two neighboring rows are then, as a result, being flipped. So you hammer this row of a memory cell, meaning aggressive, and you can do this from applications. You don't need any privileged access. This is not something that you need to do by any kind of hardware intervention. You can just do it via your application access. So some people recently showed that you can do row hammering and successfully exploit a browser remotely. So you go to a web page and someone loads a JavaScript, and this JavaScript starts aggressively hammering on memory locations and then compromises a browser as a result. So, of course, you have to, analyze the system, see roughly where, which rows should flip in which way. But once that you figure that out, the rest boils down to this row hammering attack. Yeah, so this gives you, Onur and his collaborators, they did a lot of studies on this. So if you take, they, for all kinds of reasons, they didn't want to name the companies whose products these are, but they essentially showed the vulnerabilities of these of different types of memories, because it's not. So here's the gist of it. Not all rows will be vulnerable to this row hammer attacks, but at the same time, a lot of them are. So and sort of testing and turning off the rows that are not doesn't actually work. So this gives you an idea of how many errors you get per different companies. If you do attacks on companies, and if you go out and you try to publish this, you might get sued for up to $1 billion US dollars or euros, depends on the jurisdiction in which you are sued. So be careful with that. You know, it's no, seriously. I mean, you might get a hefty lawsuit around your neck if you're not in the right jurisdiction. So in certain jurisdictions, you can do attacks, you can publish, the courts will protect you. But some countries have intellectual property laws that are not very sympathetic of such breaks. Like, don't do these attacks, for example, in the UK, potentially, right? I mean, there were lawsuits there, and researchers were banned from I mean, I shouldn't say don't do it. Well, it's your responsibility to do it, whether you want to do it or not, but it can cost you some time at least, if not money in the end. Okay, so yeah. So these are relatively simple programs, so we are not talking about something super complicated, right? So we are talking essentially a small assembly program that just hammers in particular locations. Now, the thing that you see here are cache flashes. So who actually knows how caches work? At least on a very high level, I guess all of you do, right? So cache is a small piece of memory that kind of retains the data that has been recently used, and this cache is a small piece of memory that sits close to the CPU. So it's not a part of your main memory. And of course, if this cache holds some of these values, you have to flush them, because what you want to hammer at the locations of the memory. So you will flush the cache and then essentially cause the processor to go directly to the main memory and not to fetch these values from the cache. And that's how you can do the hammering. So these kind of tricks are what people have been essentially implementing, right? Yeah. So there is also a nice Black Hat talk related to this. So this you might like. One of the main reasons why I'm showing you these kind of security-related things is that a lot of people might find computer architecture somewhat boring, but they might find security sexy, and then this might be an interesting motivation for you to understand how these systems work on a fundamental level, because then you can use it to analyze the security of the systems or try to break them. Because without some deeper understanding of how they work, it's also hard to do, right? So, okay. Is this mine? Okay. Okay, so what did we go over? We went over registers, static memory, dynamic memory. We also mentioned the flash memory and row hammer attacks, and something about array organization, which I believe is relatively straightforward. So do you have any questions related to this part? I hope that it at least excites you to read something about these memories, right? Or not. Okay, then you can think of any questions that you might have while I plug in the next talk. We still have about 115 slides to go through today, so let's see. So one of the things that is maybe important to go over is the cache hierarchies and the cache architecture, right? And we already saw how data can be stored and what kind of technologies we might have. But as you have seen from this Intel video, right? Typically the computer performance essentially depends on, today, it depends almost exclusively on memory latency. So, this goes so far that today actually so I've shown you this example of Intel's memory, new memory, but there's actually more to it. People are today doing other things, right? So they are saying, okay, look, if we cannot get the memory faster, and if we cannot get it closer to the CPU, well, what would you do if you cannot bring the memory closer to the CPU? Yeah? Yeah, you can bring processing to the memory. So one thing that you can do, you can bring processing to the memory. So how would you do that? So what your colleague mentioned makes sense. You'll bring processing to the memory, but what does this mean concretely? What would you actually do then in your system?
Allowing certain instructions, simple instructions, to be performed right in memory without having to load and save the values.
Yeah. So essentially, you would do that, right? You would take some simple processing that you believe might be done. So let's say this could, the abstraction that you can have in your mind is that you would take memory. So if this is your memory here, and you might have different memory cells, right? And now this is your CPU here. Sorry, memory arrays, right? You have your CPU here. Well, maybe what you can do, you can essentially have some small CPUs here. Maybe they're really not general purpose, full-blown CPUs that sit here. Maybe there are some stripped down versions of CPUs that don't have as many instructions, and you would get them close to the memory. And now when you're running something here, you can say, hey, why don't you run this for me, right? That's actually a new instruction called hey, like hey you. So, and then this CPU here would run some operation and interact with this memory. And that's what you will find these days under in-memory processing, right? Where this can bring you some benefits because you brought computing close to memory. So the whole game is really about bringing things closer together so that the latency is reduced. And the main reason for that is because if you take some basic textbook on computer architecture, you will typically say, okay, memory can be accessed in one clock cycle. So this is what I have in mind. I'll just launch a request and get my data, and then I continue processing, right? But of course, this hasn't been the same, right? This hasn't been true for a while. So if you look at the speeds of the CPU, that have been increasing over the last years, the memory really didn't keep up. So the latency, the access to memory didn't really keep up. And so this gap here is obviously what Intel, with its technology, is trying to close, what in-memory processing is trying to address, but also more traditionally what cache architectures are trying to address. So we know that certain things are fast but small, and certain things are large and slow. I think this is the analogy. I mean, this is something that almost you don't need to explain to people because it somehow applies also to the physical world, somewhat. So large things need a lot of energy to move, and they're typically slow, and the other way around. So here, this gives you some sort of access times, you know, hard drives having huge access times, DRAMs having smaller access times, SRAMs having even smaller access times. And so what can you do? Well, again, we have some principles here that we can use in order to build some more performant systems. So we can exploit, let's say exploit somehow feels like abuse. So we can use locality to make memory access fast. So either temporal locality, which means if something was accessed recently, you kind of assume that it might be accessed again. So this is like you're running something in a loop. There might be something that will keep on coming again and again, right? So you analyze your code and you say, well, certain types of data will be accessed many times. So why don't I bring this data into a memory that's small and fast closer to my processor? So you can keep recently accessed data, or you can say, I'm very smart, I have a machine learning, artificial intelligence, big data mechanism that will tell me what should be close to the memory, close to the CPU, and that's the type of data that I'm going to put in the cache. And literally, that's what the research in that area is, right? I mean, you have to be smart about you have to do predictions in terms of what will be accessed next, because that's the thing that you want to keep in a small memory that's close to the CPU, and that's where you will get instant access to the data. And also, you can leverage spatial locality, which is another observation related to the programs that we execute, which is that, well, if you're playing a video, or if you're listening to some music, or if you're processing some data that like that, then obviously this data might be stored in adjacent memory locations, and now you can anticipate that the next memory location will be needed in the next step, and therefore you might decide to load it in the cache, meaning load it in this memory that's fast, and bring it closer to the CPU. So you cannot make the cache big and fast, so it's small and fast, and you have to play this prediction game now in terms of spatial locality. And that's what we are going to then look into tomorrow, right? To see how we can leverage these, how we can use these kind of principles to build caches, and then also how to build, and then essentially virtual memory works in the same way as cache, except that it's a game between your drive, your hard drive, and your memory, right? So in some sense, you are again playing this kind of game of caching, right? In just on a different scale and with two different types of medium. Very good. See you tomorrow.